Hey, welcome back to AP Physics 1 with Mr. Iqbal. Today we're going to be looking at Lab 13, which is titled, I guess, the conservation of angular momentum. This is really a continuation of Lab 12 in the sense that we are going to be looking for the moment of inertia of an unknown object. In this case, a notebook. So we are going to try to determine what the moment of inertia of this object is experimentally, but instead of using dynamic rotations or rotational dynamics or rotational energy, we're going to be using, as the title implies, the conservation of momentum. And so to determine this experimentally, this is going to be the setup. So our goal at the end is to find I of the notebook experimentally. And our setup is going to be pretty straightforward. We're going to have a platform that has an initial speed omega naught, and it's just spinning. And we're going to take the notebook that wasn't spinning, and we're going to just drop it right on there. Like, we're going to bring it really close, so there's no speed here, but really there would be no angular momentum anyways from this object. We're going to slowly bring it until it hits the platform. So just right under there. And so at the beginning there was no angular momentum for this. There's going to be angular momentum for the rotating platform. Afterwards, the platform and the notebook that's on top of it are going to spin with some final speed. And this is a perfectly inelastic collision because they stick together. So they stick together and then they're going to spin with a slower speed. Just like if you had an object that wasn't moving and then you had an object that was moving, they hit each other, they move together as one unit, but with a slower speed, it's going to be something similar to that. And we can show that by using the conservation of angular momentum. There are no outside forces at play here. There's a little bit of friction, but that'll be your error. And then we can just write down the angular momentum before is equal to the angular momentum after. The angular momentum before is going to be the angular momentum of the book times the velocity, spinning velocity of the book in the beginning. So we'll put a little knot there, a little knot there. And we're going to add to it the angular momentum of the platform times the angular momentum, not the angular velocity, the angular, the angular momentum of the platform, which is the moment of inertia of the platform times the angular momentum, angular velocity of the platform, initial. There we go. And I guess we could put that there, P naught, if you want to. So we'll actually know this value here because we're going to be putting it on a Pascal sensor, and so as the object spins, it'll read out what the angular spinning speed is, or the angular velocity. So you'll be given that value right there. We also know that in the beginning, this doesn't have any angular momentum, so that term would go to 0. Now at the end, just like two masses sticking together, you can add up all the momentums together. So it'd be the momentum, the moment of inertia. So it'd be the moment of inertia of the platform plus the moment of inertia of the book, and that's going to equal the final spinning speed because they're both going to be, as a unit, spinning at the same speed. You can factor out the omega final. What do we do from here? Well, our objective is to solve for the moment of inertia of a book. So isolate IB. Let's see, what could we do? You got omega final. I'm going to divide out the omega final first. So we get I of the platform times omega initial of the platform divided by the final omega, like that. And then we can subtract out the moment of inertia of the platform, and that should give us the moment of inertia of the book. So there we have it. You've got this little ratio here, which should tell you what it is that we're going to be doing, what we're going to be graphing. We're going to be looking at what the spinning speed on the graph says before the collision and the spinning speed of the after. Now, how would I graph this? I'm just going to do y over x. I mean, technically, this is the variable that you're going to be messing around with, and then this is the change that's going to affect it, or the independent-dependent variable. But I'll write it the other way. I don't really care. So we'll put omega final in the x-axis, and omega of the platform initial in the y-axis. And then, you can plot those points. We'll do it for different spinning speeds. And once you've got those points there, you're going to get the slope. And then the slope, just like we've been doing, is going to equal omega of the platform initial divided by omega final. And so that's what the slope is equal to. So if you wanted to solve for IB experimentally, what you're going to be doing is IP times the slope minus IP, and that's going to equal the thing that we're looking for. So the next thing to do is then ask yourself, well, what is the moment of inertia of the platform? What is IP? That's going to be given to you, and I'll put it up right now. All right, so what is IP going to be, the moment of inertia of the platform? Well, there's going to be two parts to it. The first part is this little platform that it's going to be on, but the platform also consists of this little pulley right here. So we need to figure out what the moment of inertia of this is, and then also the moment of inertia of this object that locks into place, which allows everything to rotate. So we'll find the moment of inertia of this first. We'll call it I disk. I disk is equal to, let's see, I have it all down here, and I'll just tell you what they are. Well, the disk is like a cylinder, so it's going to be 1/2 mass of the disk times the radius of the disk squared. And so the mass of the disk is equal to 118.4 grams, and the radius of the disk is equal to 9.5 centimeters. And the other thing you want to know is this little plastic piece right here. And the little plastic piece, we'll call it I of the little plastic piece, PL. And that's going to be equal to, well, that's also going to be a cylinder. So it'll be 1/2 mass of the plastic piece times the radius of the plastic piece squared, where the mass of the plastic piece is equal to, the mass of the plastic piece is 6.9 grams, and the radius of the plastic piece is equal to 5 centimeters. So figure out what the disk is, figure out what the plastic piece is, and then you've got the moment of inertia of the platform. The moment of the inertia of the platform is equal to I of the disk plus I of the little plastic piece. Just a quick warning, these aren't in SI units, so you got to convert grams to kilograms and centimeters to meters. So do that, and you'll have these two, and then you've got I of the plastic piece. So there's just one more thing I have to tell you before we begin the actual experiment, and that is, what is the theoretical value for I of the book? Remember, our goal is to figure out experimentally what I of the book is equal to, but what's the theoretical value, so that way we can, look at our percent errors later on. It's going to be given by this equation right here. So the theoretical value of the book is given by 1/12 the mass of the book times the length of the book squared times the width of the book squared. So there is the equation for the theoretical value, and I wrote down what those values are going to be. So the mass of the book is equal to 413.5 grams. The length of the book is equal to 23.1 centimeters. And the width of the book is equal to 15.3 centimeters. So given that, again, make sure it's in SI units, so convert everything to kilograms and meters. You will get the value of the theoretical value of the moment of inertia of the book. And now all that's left to do is to do the experiment and then verify our conclusion. I just want to point out one last thing, though. This equation is only true for a very thin rectangular surface. Now this is rectangular, it's kind of thin. If you wanted the actual value, you would have to add a little bit more to this. So that's something you might want to talk about during your error analysis at the end of the lab. But I just wanted to point that out. So this is a good approximation, but it's not the actual. We're just going to call it the actual. All right, so let's begin. All right, welcome back. Now we're going to be doing the actual lab. As you can see on the other screen right here, here's the platform. We'll be rotating it. As soon as I rotate it, I'll hit the start button, and it's going to slowly decay a little bit because there is some friction. So what I want you to do is to look at the angular velocity right before I put the book and then right after I put the book. Those are going to be our initial angular velocity and then the final angular velocity at the end. So without any further ado, I'm going to start spinning it. You don't want to spin it too fast, otherwise the book will fall off. So, all right, so here's trial one. I'm going to hit the record button and spin it. So spin it first and hit the record. And we'll drop the book. Hopefully it'll stay. And there we go. So hit the stop. And we've got the initial angular momentum being some value right there. I'll zoom in on a little bit. Okay, so you can record the initial angular momentum right there before it hits the book. And then the final angular velocity, not momentum, is right there. And then it starts to peak down. So let's see if I could bring it a little bit closer for you to see. I would say the final angular momentum would be like somewhere around here. And then it like spikes down. So somewhere right there would be your final angular momentum. Let's repeat with a different speed and see what happens. All right, so now we're going to do trial two. I'll spin it at some other speed. And we'll hit the record button now. And just got to make sure it goes. There we go. So stop button. So here was the initial angular speed, right somewhere about there. And then the final angular speed was probably like somewhere right there. And I'll zoom in on it. So there's the final angular speed, somewhere between right there. And that's trial two. And let's move on to trial three. All right. And now I'll give it some other spin, maybe a slower one. And we'll hit the start button. And we'll drop the book gently. And so our speed, whoops, don't go any further, don't go any further, was right there. The initial spinning speed was about right there. And then the final spinning speed was right there. So this value right there would probably be the final spinning speed of that. Let's do two more trials and then we'll call it a day. All right, now comes trial four. Forward. And stop. And so our initial spinning speed was right there. I can't really spin it any faster, otherwise the platform will fall right off. So there was our initial speed, something right there. And then our final speed was, can we zoom in on it a little bit more? Here we go. Something about right here. And then it starts to decay out. So that's trial 4. We have one more trial to do. Okay, so we're on trial 5. I'm going to give it a spin. Make sure it's not vibrating. And we'll hit the record button. And I'll do the best I can to get it right at the center. And there we go. So I'll hit the stop. And let's take a look at our values. Here is the initial speed, spinning speed, and then the final spinning speed. Oops, sorry, not there. Here is the initial spinning speed right here. And then the final spinning speed was about right there momentarily. So that's the final spinning speed there. I don't think this is going to be as accurate as the other values. So the percent error might be very off today, but do your best. Those are the 5 points. So just put them on a graph and take the slope. And as I told you before, how you can solve for I of the book and then compare it to the theoretical value. It might be off, but hey, sometimes that just happens. I'll see you in the next lesson.